Hello everyone, today I'm going to be talking about hashing. I'm Roshan Naik and I'm doing this as a part of my COQ course. So let's begin. I would like to give you a problem first before delving into the actual definition of hashing and its applications, just to better appreciate the usefulness of hashing and the importance of it. Let's say you were given a situation as the following. You need to keep a track of all the students, keep a list, a recording of all the students enrolled in the institute. It could be your own institute, for instance. Um, let's say each one of these students is identified by a unique ID, student ID. Now, while manipulating this record, the three most common problems that pop up are obviously insertion, deletion, and search. That's how you manipulate the records. Now, how do you go about storing this record, this list of objects? The first way is by using an array. This is probably the simplest and the most straightforward way, is you create an array of all the students. Every time you get a new student, you create a new record. You just need to append it to the end of the array. Now search in this case takes order n, because you need to start at index 1 and keep checking every element till you find your desired student. Deletion also takes order n, because you need to search for the student you want to delete and then delete him. Now you could also take the example of linked lists for implementing this, but again linked list would be very similar because you're storing it as a list. Searching would take order n, insertion would just take order 1 because you just need to append it to the end of the list, and deletion again the same, order n. What could be another possible solution? Well, you could think of sorted arrays. If you have a way of sorting or a way of ordering two students, then you could sort the whole array in n log n time. Now you could keep a sorted heap throughout the whole process. Every single time you add an element, insertion, it takes order n because you're maintaining it as a heap, as a tree structure. Searching for the element also takes worst case complexity order n, log n, and deletion also takes log n. So this is much better than the previous idea, which was of using linked lists or arrays. But still, can we get to something better? And there is a theoretical way. There is a hypothetical solution which does all the three operations in order 1 just instantly, and that is by having a sort of a lookup table. The idea of lookup table is that you can just look for the particular student ID and get the object straight away without having to do any computation at all. So this makes search order 1, insertion order 1, and deletion order 1. But obviously, how do we go about creating such a table? First of all, this table has to take a particular value, an input value like a key, like the student ID, and give me a pointer to the object instantly. Now, we could have a table like that, but we need to keep in mind that the array index has to be an integer between 0 and the size of the array. It can't just be a random piece of text. So you can only access an array element through its index. So we need a way of mapping the student ID to an index into the array. And that's how the idea of hashing is born. So a revised solution for this problem is you have the student ID, right? 2015 CS10229. This is just an example. This is my ID. Now, if you had a table that had all permutations of the student ID, all possibilities, every character could be anything. So you're allowing for digits 0 to 9 and alphabets A to Z. So then there would be a total of 36 by 11 such students. If the length of a student ID is fixed to 11 characters, you would have 36 by 11 possibilities. So you could keep a record, an array of 36 by 11, and just map everything, every student ID to that straight away. It's easy. But we can trim the size of this down. Obviously 36 by 11 is not feasible at all. It's a very large number. So we can chop off the first two characters, 2, 0, because probably we'll have no students before coming in before 2000, so they'll all probably be after 2000. But we could also replace the two CS characters with a two-digit integer, something between 0 and 99. Now this could be further improved because uh, our institute might not be having exactly 100 branches. Now CS corresponds to a branch code, but then the total number of branches our institute might have might be way less than 100, maybe about 30 branches to 40 branches on average. So we can even shrink this down even further if we were not using a 10-bit integer. If we were using something, if we had a different base system to identify integers, maybe we could have brought down this value much smaller and taken up less space on the array table. So that's where you get the idea of hashing. You want to be able to get an array index from a given input. It could be a student ID, it could be anything else, it could be a name, a student name. You could have a student name. Assuming every student name is different, you could create a function that would map your student name to an index, and that's what the whole idea is about. So obviously this helps you out a lot. It's like a lookup table, but the only thing that differs from a lookup table in this case is you have a function, a procedure that takes your input, takes your input string and gives you a key, a hashed value that is the pointer in the array. So that's the only overload. If you had to sum up hashing in one sentence, it would be this: mapping data of arbitrary size to data of fixed size. And this mapping takes place by the help of a function that we call hashing function. It just takes your key, which is your input value, and maps it to the corresponding address in the array. What's desirable in a hash function? Now, you obviously can't have a hash function that takes infinitely long time to compute. You would prefer it to be simple, easy to compute, preferably order 1, have no overload on the time complexity. And another important property is that it should map have unique hashes for every key. It should distribute the keys evenly in hash table. It shouldn't point many keys in the same region of the hash table while leaving several other paths empty. So you want the hash function to evenly distribute out all the keys, but not clutter them in one particular region and create too many collisions of keys into the same cell. Let's have a look at some examples. Our first example is just a simple function that takes the integer value of every character and sums it up. Takes the mod n, where n is the size of the hash table, because if the sum exceeds or overshoots the size of the array, then you need to loop back so that you stay within the hash table. Your hash table can't be infinitely big. It's a limited size in the memory. Now this is simple to compute. This is very simple to compute, but the problem with this is it doesn't give any preference to order. So two things can be get mapped to the same box, hash, and let's say ash, ASHH, or similarly with trash and stash, they both point to the same cell. That's not desirable. Another idea is if you have a given integer string, you break it up into parts. You take each of the individual parts and you perform some sort of an arithmetic operation on it, and then mod that with the size of the table. And another example would be mid-square function, where you take that input key, you square it, and take a segment of it and use it as the index. Now then the fourth method is some sort of a polynomial way of doing it. So you have an input polynomial, let's say 1 plus 2x plus 3x squared plus 4x cubed, and you compute the value of this polynomial for the given input. If you can represent the input as an integer, compute the value and mod that by n. So that's also a pretty good procedure. But the problem with all these procedures is that you can't guarantee that it has a unique hash value for different keys. That is never guaranteed in any of these cases. And the whole point of a hash function is that it's got to be simple, it's got to be easy to compute so that you can quickly retrieve the point. But because of that, we can't always ensure a perfect hash function that takes an input and maps it to a completely a new unhashed to a new point in the array table that's never been accessed before. It can't guarantee uniqueness. This is the third point that was stated here: unique hash for every input key. That's hard to get. So that creates, because of that, we tend to get a lot of collisions, and collisions are uh, also happen when the size of your hash table is smaller than the number of keys. If you have no idea of how many keys are going to come and you have a fixed size hash table, then obviously collisions happen. Now, how do we deal with collisions? That's a pretty important question, and there are two popular methods. We begin with chaining. Chaining is a very straightforward idea. When two different elements map to the same cell, you basically create a linked list out of in that cell itself. You append it to the end of the list. So in this particular example that's given here, you have an element 50 that gets stored at index 1, and then some point of time in the future another element 85 comes in that's also mapped to the same index 1, but 50 is occupied. So you just create a linked list out of that cell and append 85 to the end of that list. And next up is open addressing. Open addressing is a much more popular, I would say it's much better than chaining, but you would uh, these two, chaining and open addressing, are used in different situations. Open addressing is very different from chaining in that it requires the size of the hash table to be greater than the number of keys. Open addressing doesn't work when the table size is smaller than the number of keys, because in this case we are not creating linked lists out of cells. Instead, we are trying to find a different spot in the list itself to accommodate the cell, to accommodate the key. So that's what's mentioned here. The collision is resolved by probing or looking for alternate locations in the array. So in this case, the element was just appended on to the end of the already present element. Now in open addressing, we're not trying to do that. We're trying to find another space in this that's unoccupied and place it there. So obviously there has to be a procedure of looking for alternate places. You just can't randomly go and place it at wherever you like. So there are there's infinitely many ways of probing a hash table. To get the sense and the idea of probing, we'll look at three most commonly used ones: linear, quadratic, and double hashing. Linear probing is pretty straightforward. So let's say I have my element 50 present at index 1. Next, I get another element 85, again pointing to index 1. Now since index 1 is occupied, I jump one cell ahead. I jump to index 2. And if that is unoccupied, I place my element there. Even if say 2 was already occupied, then I jump another cell. I go to index 3, see if that's occupied or not. Even if that is occupied, go to the next cell and place it at the first cell I find that's unoccupied. Another type of probing is quadratic probing. In linear probing, we are jumping one cell at a time. In quadratic, we jump one cell, then 2 square, 4 cells, and then 9 cells, and so on. So we'll be jumping I power 2 slots every iteration. Double hashing makes use of a second hash function. So basically, if the first hash function doesn't work, you apply a second, which is usually a much more complicated hash function, to get another slot. So you add the second hash value to the first hash value and go to that index. If that is filled, then add uh, you do hash x plus 2 times hash 2x, just as it's mentioned here, and check that. Even if that is occupied, then you do another hash and you jump another hash 2x times, so on. Now, an important thing here is How do you deal with deletion? Finding an element is straightforward. Even inserting an element is straightforward. It's been covered. What do you do when you're deleting? Now, deleting is a bit tricky. Now, to get a sense of what happens during deletion, let's look at this example. In this example, we have a hash table, and the hash function is simply modulo 7. So very straightforward when we are just inserting, deleting, searching for integers. So nothing too complicated. We start by inserting 3. 3 goes in its corresponding place, which is at index 3. All fine. Next we insert 10. So it goes, looks at 3. 3 is not present. 3 is already occupied. So jumps one cell ahead, goes to 4, puts 10 and 4. And now it's important to note that in this example we are using linear hashing, but the same concept can be illustrated through any other type of probing. So next we insert 17. Now 17. It goes, checks at 3, occupied, jumps one cell, goes to 4, occupied, jumps another cell, 5, it's empty, so puts it there. Next we delete 10. So we go to 3, occupied. We go to index 3, it turns out it's not the same as 10. So we jump one step ahead, go to 4. Index 4 turns out to have 10, so we delete it from there. All good. Now we search for 17. While searching for 17, we go to index 3 first, see that it has 3 in it, not 17. So jump an index, go to 4. Now 4 is empty. So would we terminate our search here itself? Now if we would terminate our search here itself, then we would be giving a wrong result because 17 is actually present. But what happened was this cell 4 previously had an element in it, but it got deleted. So it is possible that my element 17, while being inserted, jumped over the index 4 because maybe during its time of insertion cell 4 was occupied, but after insertion maybe cell 4 got deleted, so that's why it's currently empty. So it's better to mark a deleted cell with some special character. In this case I've just colored it yellow for identification. So here I color the cell yellow to indicate that an element was previously present there but it got deleted. So now when I get to the cell, I know that there was some element previously present there. So maybe my 17 is there up ahead down the list. So I continue my search. Now if it was not marked yellow, then I know that it was always empty. It was never occupied by a cell. So there's no chance my 17 could have entered the list. But if it is marked yellow, that means an element was present there previously, but then later got deleted. So there is a possibility that I'll find my 17 up ahead. So I keep searching. Okay, let's look at the differences between chaining and probing. Now chaining takes up some extra space. It doesn't guarantee order one search because uh, if you have a very small hash table and you have a lot of mappings happening in the hash table, you would end up with an array of linked lists, and that's not really desirable because when you map to an array index, you'll again be traversing the linked lists, and that'll be order and complexity. So that's too bad. But this is usable when you have no idea how many keys you're going to get. If you have infinitely many, like millions or billions of keys coming in, then it's better to use chaining, because you have to preset the hash table size before carrying the process. And it's not sensitive to the hash function or load factor pretty much, because it can manage a lot of keys by creating linked lists, by creating extra space. Probing, on the other hand, doesn't use extra space, and in a way is much faster than chaining, because chaining you might end up getting stuck in a linked list and you would have to traverse the whole linked list. And probing, it's not like that. And in probing, you don't use extra space. It has much better cache performance, uh, as everything is stored on one single array. There are no linked list. But with probing, it's very sensitive to your load factor. Load factor is just the ratio of the table size and the number of keys. Now you would prefer the load factor to be around 0.75 or less than 0.75. Anything higher than that would be somewhat dense, and maybe your hash function wouldn't be able to handle such density, or would create too many collisions. So probing is highly dependent on that. Probing on average, or almost all the time, performs your operation in order one if you have a good hash function and if you have a decent enough load factor, like I said, 0.75 or below that. And better use of space, obviously, it doesn't take up extra space. Alright, now that concludes collisions, and yeah. So now that I've spoken about the principle of hashing, the whole purpose and the intent of hashing, which is to simplify lookup and to easily manipulate large data sets, we'll have a look at some of the other areas in computer science in real life where hashing is used. Now, hashing turns out to be a very important procedure, a very important concept. It's not just used in looking up tables and manipulating data sets, but is also used in cryptography, in hiding information, while sending information from A to B. Messages get encrypted so that no one in between can listen into the conversation that A and B are having over a network, wireless communication, or any such thing like that. And the idea of hashing goes even further. It is used in so many areas of problem solving where solution of problem can easily be found out if you had some sort of an implementation of hashing. It's used in areas like Bloom filters, geometric hashing, and even in the designing of caches. I highly suggest you go through or you look up these applications online when you have the time for it, because they're really interesting and intriguing in and of themselves. Cryptography, which is one of the biggest branches of computer science that deals with hiding and safely encrypting data to transmit information, also heavily uses the principle of hashing. Now, I'll talk a little bit about cryptography to give you the basic sense of how hashing comes into play in the field of cryptography. So, in cryptography, the basic idea is to send a message from A to B. Let's say Alice and Bob. Bob is trying to send a message to Alice, but if he just sends the message straight away without hiding it, anyone in between who gets hold of the message can read the sensitive information that Bob is trying to convey to Alice. Maybe he's trying to send a password or something like that. So you need to be able to encrypt Bob's message. And Alice at the same time should be able to decrypt the encrypted message back so that she can read it carefully. Now, one of the ways of doing this is by the use of a secret key. So now this key has to be shared by shared between Bob and Alice before the process of sending the information. But there are newer methods that don't require the sharing of a key prior to the exchange of the message. But however, the idea always makes use of a secret key, and the hashing function that's employed is somewhat very complicated. It could be something like take the input as an integer, and it could take an exponent of it, some power of the input, and so that generates a very complicated hashed value that's hard to decrypt straight away. So the hashing function is designed in a way that it makes use of the secret key to create a hashed value that's hard to decrypt. Only with the secret key you'll be able to decrypt it instantly. Without the secret key it would take generations. I mean, the only feasible way to decrypt the key without knowing the secret key would to try every possible combination of the input, every possible input, and see if the hashed value matches this value here. So there are a number of different hashing functions that you can use to encrypt the data, and each hashing function has its own speciality. Even when you're saving passwords in a website, when you're logging in, your password doesn't get saved as a text, but it gets saved as a hashed version of the text. You could use so many different hashing algorithms like MD5 hashing. Each one has its own complexity, has its own uniqueness, and its own speciality. So the password gets saved as a hashed value. So even if some hacker gets access to the table of passwords, he'll just be looking at hashed values and not the actual text password. So he can't convert the hashed value back to the original piece of text. Only you can, because you know your password, and whenever you log in, your password gets hashed immediately using some sort of a complicated hashing procedure, and you get the hashed value, and then the hashed value gets compared to see if it's the right password or not. So that was just a brief discourse on hashing, and I hope this was understandable and you were able to get the essence and the meaning of hashing and why it's used so heavily used in our world day to day. And with that, I will conclude my talk on